What produces a magnetic field? Because an electric field is produced by an electric charge, we might reasonably expect that a magnetic field B is produced by a magnetic charge. Although individual magnetic charge, called magnetic monopoles, are predicted by certain theories, their existence has not been confirmed. How then are magnetic field produced? There are two ways. One way is to use moving electrically charged particles such as current in a wire to make an electromagnet. The current produces a magnetic field that can be used, for example, to control a computer hard drive or to short circuit metal. In chapter 29, we discuss the magnetic field due to a current. The other way to produce a magnetic field is by means of elementary particles such as electrons, because these particles have an intrinsic magnetic field around them. That is, the magnetic field is a basic characteristic of each particle. Just as mass and electric charge or lack of charge are basic characteristics, as we discussed in chapter 32, the magnetic fields of the electrons in certain materials add together to give a net magnetic field around the material. Such addition is the reason why a permanent magnet, the type used to hang refrigerator doors, has a permanent magnetic field. In other materials, the magnetic fields of the electrons cancel out, giving no net magnetic field surrounding the material. Such cancellation out, giving no net magnetic field surrounding the material. Such cancellation is the reason you do not have a permanent field around your body, which is good because otherwise you might be slammed up against a refrigerator door every time you passed one. Our first job in this chapter is to define the magnetic field B. We do so by using the experimental fact that when a charged particle moves through a magnetic field, a magnetic force Fb acts on the particle. The definition of B. We determine the electric field E at a point by putting a test particle of charge Q at rest at that point and measuring the electric force Fe acting on the particle. We then defined E as E is equal to Fe over Q. If a magnetic monopole were available, we could define B in a similar way. Because such particles have not been found, we must define B in another way. In terms of the magnetic force Fb exerted on a moving electrically charged test particle. In principle, we do this by firing a charged particle through the point at which B is to be defined, using various directions and speed for the particles, and determining the force Fb that acts on the particle at that point. After many such trials, we would find that when the particle velocity v is along a particular axis through the proportional to v sine theta sine phi, where phi is the angle between the zero force exists and the direction of v. Furthermore, the direction of Fb is always perpendicular to the direction of v. We can then define the magnetic field B to be a vector quantity that is directed along the zero force axis. We can next measure the magnitude of Fb when V is directed perpendicular to that axis, and then define the magnitude of B in terms of that magnetic force.